Okay, so in this video here, we're going to talk about Taylor polynomials. So we went over what a Taylor series was, right? So we define a Taylor series, right, to be the series here defined in this manner, right? And from 0 to infinity of f to the n of a over n factorial x minus a to the n. Right, so that is a Taylor series, right? It's the representation of a function using this formula here, right? Now, there is a way that we use not necessarily the whole series, but just the partial sum of the series, right? And it turns out the partial sum is an actual polynomial with a finite degree, a degree of n, right? Depending on what the nth partial sum is, right? So the nth partial sum, right, that gives me the nth, or we're going to call it nth Taylor polynomial. Right, so P n of x is defined as f of a, whatever the center is, plus f prime of a, x minus a, plus f double prime of a, x minus a squared, etc. Okay, so we'll start off with an example, right? So let's say for this example here, I want to find the P0, P1, P2, and P3. So sorry here, let's see, P0 of x, P1 of x, P2 of x, and P3 of x for f of x is equal to 1 over x squared at the value x is equal to 1. Okay, so these are the Taylor polynomials, right? Centered at 0, right? The specific Maclaurin polynomial. But here, the Taylor polynomial centered at 1. Right, so the first, or the 0th polynomial, is simply just the first term here, right? So really, it's just f of 1, right? The function value, so it's a constant, right? It will always be, the 0th polynomial will be just a constant evaluated at the term, very basic, right? Looking at this f of 1, so that is 1 over 1 squared, which is 1. Right, so that would be an approximation to 1 over x squared, or, excuse me, centered at 1, right? So notice here that both the Taylor polynomial and the function have the same point in common, right? Now, it's not a good approximation, but it is an approximation, right? As we'll see after we find these, we'll graph them, we'll plot them all on the same coordinate axis so we can kind of see how close they approximate the function. All right, so now I want to find the first Taylor polynomial, so that is going to involve the first derivative. So the first derivative, so x to the negative 2, so we'll have negative 2 over x cubed, right? Evaluated at 1, f prime of 1, that is negative 2. Right, so to build my P1 of x, now one thing to notice here, P1 of x is P0 plus just the next term, right? The next term is f prime of 1 over 1 factorial x minus 1. Right, so it's P0 of x, so we get 1, right? F prime of 1 is negative 2, so minus 2 over 1 factorial x minus 1, right? And this quantity is just 2. Right, so here actually, let me just write that as 2. Okay. All right, so that's our first polynomial. Now the second, P2, right, I need the second derivative. So second derivative of x is going to give me, so that's the first derivative. Second derivative is going to be positive 6, right? So negative 3 times negative 2, 6 over x cubed, and f double prime of 1 is simply just 6. Okay. Excuse me. Okay. Okay, so then here are P2 of x. Again, it's simply P1 of x plus f double prime of 1 over 2 factorial x minus 1 squared. Okay, and then P1 of x is just 1, 2x minus 1. And then 6 over 2 factorial is plus 3, x minus 1 squared. All right. And then our third polynomial P3. So f triple prime of x gives me a negative. So we have, sorry, I got a bit of a mistake here. The second derivative is 4. Okay. All right, I forgot to subtract the 1. Forgot to apply the power rule here. All right. So then that means here for our let's go back here. F prime, f double prime, 4. Okay. So f triple prime is negative 24 over x to the 5th, and f triple prime of 1 gives me negative 24. Okay, and then now building our third Taylor polynomial. Again, it's really just a previous one. Here we add f triple prime of 1 over 3 factorial. Okay, and then it's x minus 1 cubed. Okay, and then here we see when we plug that in, we get 1 minus 2, x minus 1 plus 3, x minus 2 squared. And then here 3 factorial, negative 24 over 3 factorial, what is that, 3 factorial 6, so 4. So minus 4 x, excuse me here, x minus 1 squared minus 4 x minus 1 cubed. Okay, and then we can start to see just a general pattern for the nth degree polynomial kind of arising here. But here we just asked to find the first 3 Taylor polynomials. Now, if we want to graph them here, so here we see, all right, our f of x, here the original graph. Here, I'll turn all of these off here. Okay, so we have our function f of x, 1 over x squared. I use the 0 polynomial here, so just the function value. Again, not a good approximation, right? But it is an approximation. And then as you see, each time I increase my degree of my polynomial, I get a better approximation, centered around 1, right? There's like an interval surrounding 1 where it's a good approximation, right? But not much outside of it, right? At least for the lower degree polynomials, right? As we start to increase the degree, we see we increase the approximation. There's a better approximation involved, right? Okay, so that is a Taylor polynomial for the function 1 over x squared. All right, let's do one more example here. So now we're going to find a Maclaurin polynomial, right? And all that means is that it's centered at 0, right? So I'm going to find the Maclaurin polynomial. Polynomials, right? So same game here. P0, P0 of x, P1 of x, P2 of x, and P3 of x for f of x equals to 1 over 1 plus x. Okay, so again, since it's Maclaurin, what tells me the center is 0. Okay, so my 0th polynomial, right, it's just a constant evaluated at 0, so that is 1. Okay, so now let's find our P1, so that involves the first derivative. So this will be, so think of 1 plus x to the negative 1. So negative 1 over 1 plus x squared. Whole thing evaluated at 0. F prime of 0 gives me negative 1. Okay, so that means that P1 of x is negative, excuse me here, what is going on here? All right, 1 minus, right, 1 over 1 factorial x, right, or just 1, right? Minus x. All right, so here, second derivative, and then we start to see kind of patterns as I keep taking derivatives over and over here. So negative 2, so we can think of this as positive 2 now, over 1 plus x to the third power. F second derivative of 0, we get 2. Okay, and now the second polynomial here is right, the first two, so 1, or the previous one, which is 1 minus x, and now we're back to being positive, and here we get f double prime of 0, which is 2 over 2 factorial, right, x squared, and notice that's 1 again. Okay, and then we start to see that we are going to have this pattern emerging where the top, right, you can think of this top is 1 factorial for P1. Here 2, also 2 factorial. Right, and we'll see this pattern will start to emerge where if I take the third derivative at x, this will be negative, right, 2. But now we have that 3 over 1 plus x to the fourth. Right, and if I keep going, right, I keep adding that factor, right? So the derivative itself has that factorial pattern showing up, right? F triple prime of 0, that is negative 2 times negative 3, right? Or 6, or 3 factorial, however you want to represent it, right? In other words, what this looks like is RP3. So we get 1 minus x plus x squared, back to minus, right, 2 times 3, 3 factorial, right, we get this quantity essentially being 1, plus x squared minus x cubed. All right, so we get this alternating powers, alternating signs for our powers. So if we want to write the nth polynomial using sigma notation, right, we can do here, start at 0 to the nth, here we go, let's use a different term here, let's call it k. So negative 1 to the k, x to the k, right? And this matches up, right? When it's 0, that gives me the constant 1, then 1, etc., whatever it is, it gives me that pattern here. So let's take a look at the function itself here. So let's turn all these off here. And let's reset new function here. So my f is going to be one plus x. Okay, and centered at 0 here. Okay, so when I make center at 0, so change that. Okay, and again, first one, not that good of an approximation. But as I start, again, increasing my degrees, right, that approximation gets better. Right, and you can start to see, actually, let's, yeah, okay. So now we have that here, and then you can see each iteration, you get a better approximation there. Okay.